Okay, good morning, everyone. Good morning, Esmeralda. Okay, how did the homework go? Do you guys have any questions? Put them on chat while I give 2 minutes for everybody to join in. Okay, so as you realize, I try to remember to, over the weekend, I send you the review for the final and the time for the final. So your final exam is Thursday, May 6th, a week from coming Thursday. It's early morning. The exam will open at 7:30 a.m. Get that straight. And it will close at 10:30 a.m. Okay. And a Zoom link will be sent. The Zoom link will be put on Brightspace because I want you all in class with their camera on. So Zoom link will be put on Brightspace on the announcement page. Okay, because it's not during it's a little bit off our regular time. So I cannot use the same link for your final exam. Okay, and the exam is comprehensive, so you are responsible for everything. I will review with you next time to go just to remind you everything we did this semester. And please, go over exam 1, exam 2. That will be extremely helpful, and the review I gave you, and you will be fine, and you have plenty of time. I mean, you guys are the lucky one. Your exam is at the end of the final exam week. But get started soon. Don't wait for the last minute to get started. All right? Okay, any questions about the exam? Okay, let's take care of that. Now let's go back to your homework. Do you guys did the homework? Do you have any problems with it? Anyone? Okay, so I will do 2 problems, and then I will proceed to the last idea I would like to cover. So we'll do just 2 arbitrary problems from the homework I assigned. So it was section 4.1 and 4.2. So we learned how to solve equation where the unknown is an exponent. That's what we emphasize now. And we did some practice problem based on that. So let me do 2 problems unless you have anything specific yourself. So I'll do like number 7 from the homework. We have to solve the following equation. 7, 6x equal to 5. Okay. And I will do another one. I will do number 13 from your homework. Okay. All right. And you guys will guide me as I am doing them. So we need to solve for this x. We need to solve for this x. Okay. So what is the process that we followed? What do we do? Ideas? Please speak up. Okay, we're going to take the natural log from both sides. So we say that the ln of the first term is the ln of the second term. That's how we have to start. Okay, and then we use the property of the ln, which tells me that if you have ln of any term to a power, I can bring the power down, multiply it by the ln of a. And this would definitely give me the opportunity to take the 6x minus 3 and basically bring it down. I have to bring all the expressions 6x minus 3. And that will give me the ln of 7 equal the ln of 5. And now the idea is I need to free the x. To solve for it, I need to free it. To be able to free the x, we divide by ln of 5 both sides. I meant ln of 7. And this would give me the 6x minus 3. So I'm trying to free up the x because I need to solve for it. ln of 7. And now to make the math a little bit simple at this stage, we can evaluate this. And then I'll have a simple equation in x. So we're going to evaluate ln of 5 divided by ln of 7, which gave me 0.827. So we're going to find it to 3 decimal places. So 3 decimal places, 0.827. Otherwise, you will be doing a lot of rounding. And now we're done. Now we're going to solve for x. So we add 3 both sides. Will give me 6x equal that. It means 6x equal 3.827. And then divide by 6 across the board. Divide by 6. Okay. And this will give me x equal 3.827 divided by the 6. And this will give me 0.6378. All right. And now we can check. I mean, we can check just to make ourselves a little bit comfortable. I mean, am I doing the right thing? So to check, we have to plug in x into, so we take 7 to the power 6x minus 3, and we check, this is going to give me a 5. That's really what we are doing. Okay, so it's nice sometimes to check, just so we know what we're doing. And so it means I have to multiply this by 0.6378 minus 3, which is a mess. So first I evaluate the power, and then I take 7 to it. So I evaluate the power. I will have 6. So I'm just checking that my work is correct. 0.6378 minus 3. So the power is, I'm evaluating the power first, otherwise I'll have a mess in my hand. And then I check if I take 7 to this power. So I would take 7 to the power this number, 0.82688. And I'm getting almost 4.9997. So it makes sense. So this is gonna give me 4.997. So we are very close to 5. And I said it's the rounding that's making us not get exactly 5, but we should get very close to 5. If you get 4, it means your answer is wrong. You have to get 4.999 to make sure that you're getting something very close. Okay. All right, questions as I move on? All right, so we're going to look at 13, and then we're going to look at another problem that involved double time and half time, just to make sure we understand those, which are simple, but you have to make sure we understand them, unless you guys have specific questions. So I look at 13. What is 13? 3 times e, the number e, to the power 4x plus 2 equal 16. Okay, and we have to solve for x. So what is the first step in this scenario, please, all of you? What's the first step, quickly? Okay, we're going to isolate the exponential term. Always we isolate the exponential term. To isolate it, we have to divide by 3. So the goal is to isolate it so we can take the ln. Can I give me e to the 4x plus 2 is 16 over 3, totally isolating it. Once I isolate it, I am ready to take the log from both sides. So I will have ln of e equal ln of 16 over 3. Okay, and now we do what we always do. For x plus 2, we can bring this down. Or we can use the property. The property, if I remind you, ln of e to any power, to anything, will give me this anything back, because that's really the definition of ln. So ln of e to whatever you want is whatever you had as a power of e. Another reason for that, so that's the definition of ln, or if you apply the rule that you bring the power down, you're going to have here ln of e, but ln of e is equal to 1. So whether you use the definition, the property of ln, or you use the fact that ln of a to the n is n ln of a, you get exactly the same thing. So this is the ln of 16 over 3. So now I get for x plus 2 is ln of that. And now the rest is simple. Once we reach this stage, then I can isolate my x very easily. So now I compute ln of 16 over 3, which is going to give me 1.67. So I will find it to 1.67, 3 decimal places. So I'm going to round up at the 3rd decimal place for x plus 2. And finally, I will get my 4x minus 2. It means my 4x equal 1.674 minus the 2, which give me a minus 0.326. I divide by 4 across the board. So finally, I will get this divided by 4, which give me minus 0.0815. Okay. So that's how we solve those functions. Now we finish this before I start the new ideas by solving a problem, because we do those to solve problems where the function itself is an exponential function. So I take I'm going to pick any problem from section 4.2 and we do it. I will pick something that involves the double life or double time. And if you have any question, I will get back. So let me take, for example, number 10. Okay. So number 10 is the following. You have a town, it's growing at the rate of 4% a year. So the town is growing at this rate. So since it's growing, at some point, the town is gonna double its size. And the question is, what is the doubling time for the population of the town? Okay, so we have a town, that's the problem. So graphically, that's what we have. We have a certain town and it's growing at this rate. So we don't know what it started with, but it's just growing. So whatever, I don't know what was the initial value. So we're gonna call this initial value A because we don't know what it is. And the question is, at some point, the population will double. The population will be twice what it started with. And the question is, what's the doubling time? It means, when will this happen? Okay, that's the idea of doubling time. It means you have to find the time when the population is twice what it started with. All right, so how shall we do this problem? Any ideas? How can I find the time needed for this population which is growing? So the growth rate here, we know how fast it's growing. Every year it's grow by 4% of the year before it. So I know the growth rate. So I have an idea about how fast it's growing. How can I find the double time? Ideas? What do you want me to do? Okay, Esmeralda, can you speak up, Esmeralda? So we're going to introduce a function. What?
Yeah, I'm able to speak up.
I can't hear you.
I'm able to speak up.
What? I can't hear you also. Okay, so we're going to call f of t to be the population at time t. Okay, we introduce a function we call the population. All right, now this is an exponential function because it's growing at the rate of 4%. So what is the formula of the population? It's the initial value, which is actually don't know. They didn't give it to us, but it's not going to actually matters, times b to the t. That's really the form. Now, b in my case is 1 plus the growth rate. Because it's increasing. They're telling me it's growing. It means 1 plus the 4%, which is 0.04. So my function is initially a 1.04 to the power t. Another question is find the doubling time. Now we need to find the doubling time. It means we need to find the time t such that the population is twice the initial value. Okay, that's really what it means to find the doubling time. When is, so that's the question, when is the population 2a? So we're gonna set this equal to a and solve for t. All right, so now we're gonna solve. So at this stage, we solve exactly the way we've always solved. I have to isolate my expression. So I'm gonna divide by a across, and then the a will actually disappear. That's why they didn't give it to us. I will have 1.04 to the power 2 is equal to 2. And now I solve. I take the ln both sides. And then we're going to take the t, bring it down. I will have t is the ln of 2. And finally, I solve for t. Okay, and that's what gave me how long it takes for the population to double. And so we get ln of 2 divided by ln of 1.04, which will give me 17.673 years. Okay, so almost 17 years and a half for the population to actually double. And regardless what the starting point, whether we start with 1 million or 2 million, the time it takes for it to double is always the same, because the doubling time only depends on how fast it's growing. It doesn't really depend on what it started with. And that's when we have this exponential growth. Any questions?
Could you do a half-life one?
Yeah, what will be the scenario with half-life?
How long it takes for it to reach half
What?
of what it would be?
What will be the scenario? So I will pick up a problem from what I've assigned and I will do it. So, okay, I do number 15. Okay, so I will look at it and we do it. Okay. Cobalt-58 is a radioactive substance that decreases at the rate of 0.9742% per day. So some kind of radioactive substance that's decaying with time, and that's the rate at which it decays. The question is determine the half-life of cobalt-58. All right, so we have a radioactive element which is decaying, and that's the rate at which it's decay. And the question is find the half-life. All right, so let's do that. That's your question, right?
Yeah, I just wanted the half-life example.
Along those. So I'm going to call f of t. So they did not give us the initial value like the previous problem. You know, sometimes they do. F of t is the amount of radioactive at time t. How much it is, so of cobalt-15 or whatever this is at time t. Okay, so we don't know how much we had initially in this problem. Sometimes we do, but we know that it's decreasing. That's what we have. And the growth rate, and we have to be very careful, it's a minus growth because it's decreasing. So it's a minus whatever they give us, 0.9742%. All right. And the question is, at some point, half of it remain. The question is how long it takes. All right. So first we find a formula for f of t. What is f of t? It's the initial that we don't know, but we want need times b to the t. Now let us find the b. That's a decay. So 1 minus b is going to be less than 1. 0.9742 divided basically by 100, because that's what it means percent. So which is going to give me 1 minus 0.009742. And I just have to plug in this into a calculator. I don't know what this is in top of my head. So it's 1 minus 0.9742 divided by, so I'm getting 0.99. You guys should do the math with me. 0.258. Okay. So it means f of t equal, I'm going to keep it the same. It's going to be whatever times this number, 0.9. So it is decaying at very, very, very slowly. And radioactive element decay very, very, very slowly. So this is f of t. Now I need to have the half-life. Means now we need to find t. That's the half-life. Such that the value, the amount of cobalt-58 remaining is half what it started with. That's really what we need. So we're going to set this equal half A and solve for t. The numbers are not pleasant, but that's the real numbers. Okay, now we're back to something that with before. We divide by divide by A. And this will give me 0.990 to the power t equal a half. Now I take the ln from both sides. Zero, 258 to the power t. And then I bring my t down. And then I 0.990258. Do you think t is going to be a large number or a small number? What do you think t would be?
Would be large.
Large, yeah, because, finish the sentence.
Well, it'd be large because since it's decreasing at such a low amount.
Exactly. It's going to be large because it's decreasing at a very, 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 very slow rate. So the half-life is going to be a large number. And how large it is, I don't know. We have to figure this out. So this is ln 0.990258. And then we just plug in number, 1/2 is 0.5. So I will have ln of 0.5 divided by ln of 0.990258. And I'm getting 70 years. I don't know if anybody getting the same years. Okay. Anybody got the same answer? Anybody tried?
Yeah, I got 70.8 as well.
Yeah, okay. So it's going to take a while because the rate is very, very, very slow, right? The slower the rate, the longer it's going to take for it, the half-life for it. All right, so that's the idea of half-life. All right, any other questions? Okay. All right. Now, what we're going to talk about is that so far, so another way to write an exponential function. And the reason we write it the other way is because calculus is easier with the other way. So another way to write the exponential function. And it's very important to know both ways represent the same thing, all right? So far, we wrote exponential in the following format. So far, that's what we did. Exponential function function has the following form. So far I had the form a times b to the t or to the x, whatever we want. All right, so that's how we write exponential. Now we're going to rewrite them in a different format. Okay, we can rewrite, and I emphasize the word rewrite because I'm not going to change. I'm going to rewrite. Now we can rewrite a times b to the t in the form a times e to the kt. And I will elaborate by example, how can I rewrite that into this form? So that's really the goal, that we're going to rewrite the exponential into this format. And the reason we do that, the main reason is that for those of you who will study calculus, you will realize that working with e is much easier than working with b to the power t. So that's why we always work with the e, because it's going to be simpler for the formulas of calculus. That's why we're going to do that. But we have to learn, how can we change this into that and vice versa? How can we go back and forth between the two forms? So I will elaborate by an example, and then I will give you the rule. So suppose we have a function f of t. And this function is a typical exponential. So like 1000, let us say 1.2 to the power t. So in my scenario here, the b is 1.2. I'm going to rewrite, and I'm emphasizing the word rewrite. Means I'm not going to change anything. I'm going to just play with it. I'm going to rewrite it in this form. How can I do that? Now, let us recall that if I take e to the power ln of 1.2, this should give me what? Back to you, and quickly. E to the ln of 1.2. This should give me what back? Now you knew that last hour. I'm waiting for answers. Give me 1.2 back. It's crucial. So that's going to give me 1.2 back. So 1.2 e to the ln of 1.2 are the same. So now what I'm going to do, so it's look kind of weird, but I have to explain where the whole thing coming from. Now we're going to substitute e for 1.2 in the expression above. All right, and see what do we get. So I'm going to just substitute and watch what this will become. So now I will have f of t equal 1000, 1.2 to the power t. And instead of 1.2, I'm going to substitute this expression. So this will become 1000 e to the ln of 1.2, the whole thing to the power t. Okay? Now, one of the property of the exponential is the following. I'm going to use the following property of the exponential, which tells me that if you have any number a, let me call it a, raised to the power n, and the whole thing you raise it to the power m, okay, so something like that. Before I do it, suppose you have a square, and you raise it to the power 3. This is a to which power? How many a's will we have? Now think about it in the most easy format. I mean, I'm sure I gave you the rule. But what's the a to which power? What do we do with the power? What's a squared to the power 3? It means you take a square, you times it with a square, you times it with a square. So how many a's we're going to have? 2, 2, 3 2's. So this is going to give you 3 of them, which is a to the power 6. Okay, so property of the exponential is that in general, if you take a n to the power m, you just multiply them out. All right. Now, why I'm gonna bringing this out of the blue is because here I will have 1000 E. So E is a number. It's like the A. Ln of 1.2 is the number, which is n. And T is a number. So this is going to be written as Ln of 1.2 times T. Okay, so I rewrote it as 1000 e to the power that, which is, if I do the math, so if I take Ln of 1.2 and I pick up my calculator and evaluate it, this is going to give me 0.1823. So this will be written as 1000 e to the power 1823 times t. Okay, so this is my function, which is 1001.2 to the t. I rewrote it. As you realize, I'm not changing. I rewrote it into the form 1000 e to a certain power times t. So this, I'm going to call this k. So we call k to be this number, 0.1823, which is nothing more than the Ln of 1.2. Okay, so the k here is going to be this number. So let us a little bit recap. What did I do? I took a function that had a regular exponential, the way we know it. I manipulated algebraically, and then I rewrote it into the form 1000. So this hasn't changed, but this became e to the power kt, where this k, which is 0.1823, was nothing more than the natural log of 1.2. So every exponential function, I can rewrite it as in this format. Now, part two, before I actually kind of put them in one theorem, is the one formula is the following. So part two. Part two is the idea. So now suppose the following. Suppose somebody gave you a function. Suppose we have a function f of t is given in the following form. So suppose somebody give you the function is given in the form a times e to the kt. And the question is how to rewrite it. The question is how to rewrite in the form ab to the t. Okay, so my goal is to tell you that those two are basically the same. So suppose somebody tell you, okay, f of t is given by that. Okay, what does it mean? What I'm telling you, that's the same thing as a to the b to the t, but the question is, what's the b? I mean, what's really going on mathematically? Again, I elaborate by an example. So for example, suppose f of t is, somebody tells you, f of t is given by 1000 e to the minus 0.03t. Okay. In this case, the k here is what t is multiplied by. So the k is this piece right here. That's what we mean by the k. So the k is minus 0.03. Another question is, okay, why is this the same thing as that? It means what's the b? What's really going on? So watch what I'm going to do here. I'm going to do the following. I'm going to take this expression and rewrite it. And once I rewrite it, everything into this following form. E to power that. I'm using always the same approach. I'm using always the property that if you take any term, n to the m, you multiply the power. So in this scenario, what's playing the role of a is the e. What's playing the role of n is minus 0.03. What playing the role of m is the t. So this is the same thing as multiplying the exponent. Now I am basically done. So this is going to be equal to this piece here will be the b. In other words, let me evaluate e, this expression, and it means I'm going to pull it up in my calculator and evaluate it. and I'm going to get 0.9704. It means this could be written as 1000.9704 to the power k. So let me sum up. If a function is given into this form, e to the kt, this is exactly the exponential function we know, the one we've learned. But what is the b? The b is going to be e to the power this k. Okay, so exponential functions are going to be given to us either in this format that we are familiar with, that we've learned, or a lot of time will be given to us under the form 8e to the kt. And the question is how to go back and forth between them. So if it's given e to the kt, then I can rewrite it as a b to the t, and where the b is going to be nothing more than the e to the power k. So let me summarize this in a nice big formula, and then we will work with that, how to go back and forth between those two ideas. So summary. All right, here it is. Any exponential function, any exponential function can be written in two formats. The following format: a b to the t, that's the form, or a e to the kt. And what's the relationship between all of them? So whenever you have exponential, you're going to see it either this way or that way. And the idea is that those represent the same function. So some name and some relationship. What is the k? So if we know b, k is nothing more than the ln of b. Let me take you back here. If we know b, the 1.2, the way we got the k is we rewrote it as e to the ln of 1.2 times t. By rewriting this, then the k will be the ln of b. That's what's going to be the k. So if we know b, k is ln of b. Now, if we know k, b is e to the k. That's the relationship between them. Now, k is given a name. We always give it a name. K is called continuous. So whenever you hear the word continuous growth rate, so when they tell you continuous growth rate, when they use the word continuous, it means they want you to use the formula a e to the kt, and that's the k. And b is the b. B is what we know. B is the growth factor. Nothing changed in that. Is the growth factor. All right. So summary. Every exponential function can be written in this way or that way. How we go back and forth between them. If it's written under this form, a b to the t, and they tell you rewrite it under this format, that's the relationship. The k is the ln of b. If we know the k, so they give it to us in this form, and they told us rewrite it that way. If we know the k, the b is e to the k. So let's do two examples so we can go between them both and fast. So example. All right, for each of the function below, I want you to do the following. If the function is written in this form, I want you to write it in that form. And if it's written in this form, I want you to rewrite it in that format. So my question is, write f of t, which is, let us say, 1000.9 to the t in the form a e to the kt. Okay, so I want you to rewrite this in that form. And then I'm going to ask you a little bit about, make sure we understand the wording here. All right, how do we rewrite it? So sorry. This. How do we rewrite? What's the K? The K is, so here the B is 0.9. Means the K is going to be the ln of B. It means the K equal ln of 0.9, if we pick up our calculator, so it's equal to minus 0.1054. It means that f of t, and realize I kept equal because I'm not changing the function, I'm rewriting it. It's going to be 1000 e, watch e to which power, minus 0.1054. That's how we can rewrite it. So write this function in the form 8e to the kt. We just have to remember how the formula works. The b, that's 0.9, that's the growth factor. K is the ln of 0.9, which gives me that much. Note that we're not changing the function, we're just rewriting it. It means if you plug in a 2 in here, for example, I take t equal to 2, I plug it in here, I plug it in here, I get the same answers. I plug 5 in here, I get the same answer. So we're not changing, we're just rewriting this format. Now, what's the continuous growth factor? Just for the terminology. Sorry, continuous growth rate. When you hear the continuous growth rate, they mean the K. So that's the minus 0.1054. That's the continuous growth rate. Now the growth factor is the B. Nothing changed in this scenario. The growth factor is the B. The growth rate, not the continuous one. The growth rate is like we did before. If the growth factor is 0.9, this is 1 plus the growth rate. So the growth rate is 0.9 minus 1, which is minus 0.1 or minus 10%. Okay, so the continuous growth rate is the K. Everything else is the way we know it. Nothing really is changing. So example number 2. Please, if I turn the page fast, let me know.
Yeah, I'm still writing.
Yeah, you guys should let me know. So the idea is has to switch. And as I said, the importance of it, this is used in calculus more. The benefit of this way, which is for us, at least in this class, is that we understand it better. Because when I read it this way, I know that it's a quantity starting at 1000 and it's decaying at the rate of 10%. So we understand this better, but this is easier to use eventually in your calculus classes. That's really why we do this back and forth writing. Are you done?
Yeah, I'm done.
Thank you. All right, so let's take another example where I'm going to move you backwards. So example number 2. Okay. Question is, let f of t equal, I don't know, I'm going to make up something. Let us say it is 500 e to the power 0.2t. Okay, and the question is, write in the form a b to the t. Okay, I'm going to now go backward. All right, question number 1 is, what's the k in this scenario? What's the k? Back to you. What is the k that we're talking about? Anybody? So I write it e to the kt. What is the k in here? What's playing the role of k? Okay, anybody else? The k is what's t multiplied by. This is the K, is the 0.2. That's what we mean by the K. So I have my function f. It's 500 e to the 0.2t. So the K here is the 0.2. And the idea is I need to rewrite it in this format. So how do we rewrite it? What's the B? I will show you. You can memorize the B, or one way you can avoid memorizing it is the following. We're gonna rewrite this expression like that. And that's really what the B is. So the B is actually nothing more than E to the K. That's the B. And that's really how it come up. So this is really rewritten that way. And that's really what my B is. So which is equal to, so if I do the little bit of math, that I will get 1.2214. Okay, so it means that this is equal to 500, 1.2214 to the power t. So I took this expression, I just rewrote it. That's really what we are doing into this format. So now the language. What's the continuous growth rate? Continuous growth rate. What's the growth factor? And what's the growth rate? All right. The continuous growth rate, it means it's the K. That's what it is. So when I tell you continuous growth rate, it means the K. That's the 0.2. That's the K. The growth factor is the growth factor. It's the B. 1.4. The growth rate is how far the B is from 1. 0.14 or sorry. 0.14%. Okay, so that's really the scenario. All right. Okay, one more example, but please try to pitch in yourself. So you get this. It's not hard, it's just a language that you're going to develop. So a last example is the following. Suppose f of t equal 1000 e to the minus 0.123t. We write in the form a b to the t. We're going to rewrite that in this form. Question number 1, what is the K in the picture? What is the K here? What's playing the role of K? I want somebody beside Esmeralda to put the answers on chat. K is what's T multiplied by. What's the K in this scenario?
Negative 0.123.
Right, that's the K. Crucial to know what my K is. It's negative 0.123. That's the K on this scenario. Now, what's the B? The B is, what's the B? That's the K. What's the B? You can memorize it or you can think about it. What's the B in this scenario? It means what shall I write in here for the B? Back to you. It's the E to the power 1.23. That's really my B. That's going to be my growth factor. So that's E 123, sorry. 0.123. All right, so this is going to be equal to 1000. Now I just evaluate that. And if I evaluate it, I mean, I pick up my calculator, I get 0.8842. Okay. So that's really how this conversion is really going on. The continuous growth factor, when we use the word continuous, we're talking about the K. And then the continuous growth rate, we're talking about the K. And then everything else is the same. The continuous growth rate is the K. The growth factor, 0.8842. And the growth rate is how far 0.8842 is from 1. So the growth rate, so continuous growth rate, so that's the language, is the K, that's the K. Growth factor is my B, which is definitely, it's less than 1. So it means things are decreasing because the B is less than 1. And the growth rate is going to be negative because the B is less than 1. So the growth rate is going to be, now here always we remember, the growth factor is 1 plus the growth rate. So my growth rate is going to be 0.8842 minus the 1. And if we do the math here, we get 0.8842 minus 1. This is going to give me minus 0.1158. Okay, and that's a negative growth because the B is less than 1, make it to be a decreasing function. Right? Okay. Now, any questions? So now let me take the following problem and I'm going to add a word to the language. So suppose I tell you example. Okay. The population in Washington state. So suppose we have the following. The population in Washington state in million is given by f of t equal, no, sorry. I'm not going to give you the formula. So the population in one state in sorry, my apology. I'm going to change a little bit the setting. The population in Washington state in 1990 was 5.4 million. Okay, so in Washington state in 1995, the population was 5.4 million. And the continuous growth rate, I'm adding growth rate, is 0.013. So I'm changing a little bit the scenarios. Question number 1, find a formula for the population. A formula for the population at time t. Now, when I tell you the continuous growth rate is 0.03, it means they are giving you the K, not the actual growth rate. So it means that f of t equal, because they are telling you that's the continuous growth rate, it means they are giving you the K. So here, f of t is equal to its initial value times e to the kt, where K is to 0.013. So when they give you a problem and I tell you the continuous growth rate is that much, it means they want you to look at the formula A, e to the kt, and the K is whatever number they give you. It means my f of t equal 5.4, that's always the initial value, e to the power 0.013t. So that's the population. So I repeat, when I tell you the continuous growth rate, it means I'm giving you the K. The rest is simple. Suppose I ask you, for example, find the population in the year, so initially, this is the year 1995. Find the population in the year 2020. Okay, so in 2020, in 1995 is the year equal to 0. That's my initial value. In 1920, T is equal to 25. So the population in Washington State, according to this model, is 5.4 times e to the power 0.013 times 25. Okay. Now, how do we evaluate this number? So 5.4 times. First, we multiply those by each other just to make sure we're getting the correct number. And then we proceed. So we're going to do that. So 0.013, we times it with 25. And I'm getting that number. Okay. And then we just evaluate that. So this is going to be equal to 5.4 times. Okay, so I evaluate the rest, 5.4 times e to the power 0.325. And I'm getting 7.47 million. So it means in the year 2000, the population in Washington State is going to reach that much million. So the main idea today is this conversion between those two ways of writing an exponential function. That's really the main idea because it's going to be useful. And sometimes, a lot of times, instead of people telling you what's the growth rate, okay, they tell you continuous growth rate. And what do you mean? What do they mean by continuous growth rate? Which is, we don't fully, and we understand growth rate. Continuous is harder to understand. So when they say continuous growth rate, it means they are giving you the K. It means they want you to write the function as the initial e to the kt, and that's really the K. And once we write it in this format, the rest is simple. Okay. Right, questions? Now, at this stage, I can ask more problems, more questions. So if I stay with the same situation, part C, I can ask you, when will the population reach? When will the population in Washington State reach, let us say, reaches 8 million. Okay, when will the population reach 8 million? Now, once I have a formula for the population, so it means here we're going to set f of t equal 8 and solve for t. 40. Okay, it means we're going to put 5.4 e to the 0.013 t equal 8 and solve. Now, this problem we've done several times. We're going to isolate this term. And then we take the natural log from both sides. And then we solve. This is my power. I bring it all down. Equal ln. And then we solve for t. Okay. right, so next time on Thursday, what we will be doing is more problem along those lines, because they will be highly represented on you. They will be on your exam, so I want to make sure you guys know them, and we will review for your exams. All right, so right now you can guys start taking your quiz. It's on Brightspace. Good luck.